We are discussing weak interaction, and in the 7th video we'll talk about quark decays mediated by weak interactions. After following this video, you will know the quark decay mechanism, which is analogous to the muon decay we discussed in video 6.4, and you will know the quantum mixture of quark states which interacts with W bosons, and the Cabibbo-Kobayashi-Mascawa matrix, which describes these mixtures in the Standard Model. The coupling of quarks to the W's plus and minus privilege those between members of the same generation, but they also exist across generation boundaries. Pion decay is an example for the dominant case, where the W connects an up quark to a down quark. An example of an intergeneration decay is the Kaon decay, where the W boson connects an up quark to a strange quark. In the Feynman diagrams shown here, we have again replaced the incoming antiquarks by outgoing quarks. The ratio of the two partial rates is measured to be of order 1. This experimental result shows that Kaon decay is very much disfavored. The Kaon phase space is large compared to the pion, due to its large mass. Neglecting muon and neutrino masses, the decay width is proportional to the parent particle mass to the 5th power. The ratio is thus expected to be 100 times larger. It must be concluded that intergeneration interactions are disfavored compared to intrageneration interaction by at least a factor of 100 in the rate or a factor of 10 in the amplitude. In 1963, Nicola Cabibbo proposed a way to describe these processes. States which interact with the W plus minus are not the quarks which are listed in the periodic table of matter particles, which we presented in Module 1. The particles which interact with the W bosons are the mixtures d', s', and b', quantum superposition of the real quarks d, s, and b. The states d', s', and b' are not eigenstates of the mass operator, so they are not the real particles which evolve in space-time, but they come from a rotation in flavor space. Since this rotation should not change the number of fermions, the operator must be unitary. For two generations, the description is simplified. In the formula, we symbolically substitute the wave function of the quarks with the name of the quark. The angle of rotation between the first two generations, theta c, is called the Cabibbo angle. The mixing corresponds to a modification of the weak charged quark current. A small strange quark amplitude adds to the down quark wave function, and vice versa. As a consequence, the amplitudes of the weak interaction of quarks change. For dominant interaction of the W with the UD current, for example, the rotation induces a factor cosinus theta c in the amplitude. For disfavored interactions, such as those with the US current, a factor sinus theta c appears. The relative rates of the two types of interaction are thus reduced by a factor tangent squared of theta c. From the observed rate reduction with respect to the phase space, one finds a Cabibbo rotation angle of about 13 degrees. This consideration must be generalized to three generations of quarks. Matrix notation is introduced between states which appear in the weak charged quark current, that is d', s', and b', and the real quarks d, s, and b. The unitary matrix VCKM is called the Cabibbo-Kobayashi-Mascawa matrix after the name of its inventors. The particle data group compiles the value of its elements from many different measurements. These matrix elements appear at each vertex of the W plus minus with a pair of quarks. Absolute values are measured by comparing decay rates of each type, except for top quark interaction, where they are derived from the unitary of the matrix. The matrix elements become smaller as one deviates from the diagonal. This means that intrageneration interactions dominate the weak charged current. Intergeneration interaction jumping a single generation are disfavored. Those which bridge two generations even more. The structure of the matrix thus favor decay cascades, like the one of the top quark shown here. Note that unitarity allows the matrix elements to be complex. Therefore, a non-trivial phase angle may appear in the matrix. This factor makes amplitudes non-invariant under the operation CP, the symmetry between matter and antimatter. We will talk about a violation of matter-antimatter symmetry in the next video.